In this video, we're going to be solving problems using sinusoidal models. And by the end of this video, you should be able to write a sinusoidal equation that models a real-world problem or models a given graph, and write a sinusoidal equation that has specific features. And we'll also be using our sinusoidal models to answer some questions. So let's start with writing equations to model graphs. In our first example, a nail located on the circumference of a water wheel is moving as the current pushes on the wheel. The height of the nail in terms of time can be modeled by the graph shown. Determine an equation of a sine function and a cosine function that models the graph below. So our general equation for a sinusoidal function is y equals a times sine of k times x minus d plus c. This is what we want in the end, as well as a cosine function, so instead of sine, it would just be cosine. We need to find the values of a, k, d, and c. So let's start off by identifying some of these key features. Let's start off with a. So a is the amplitude. And the amplitude is the distance from our maximum or our minimum to our axis of the curve. So there is a formula to find this, but in some graphs you may be able to identify it by just looking at the graph. But to find the amplitude, it's our maximum value minus our minimum value divided by 2. So from our graph, our maximum is 3 and our minimum is -1. So we need to do 3 minus -1, divide that by 2. So 3 minus -1 divided by 2, that means our amplitude A is equal to 2. And now let's work on finding k. So you should know that k is not the period of your function, but it is related to your period. There is a connection between your period and k. And in any regular sinusoidal function that doesn't have any transformations, our period is 360 degrees. But in a transformed sinusoidal function, the new period is equal to 360 divided by k. Since we're given the graph, we can identify the period of this function by just looking at the graph. So to find your period, you need to pick a point where you want your cycle to start. So I'm just picking this maximum point right here at 0 seconds. So at the maximum, if we go through one whole cycle and back at our maximum point, that would be at 10 seconds. So one cycle takes 10 seconds long, and that's our period. So now we need to use that period to solve for k. So if I substitute 10 in for my period, 10 is equal to 360 divided by k, and we need to solve this equation for k. So to get k out of the denominator, we can multiply both sides by k. And to get k by itself, we would need to divide by 10. So k would just be equal to 360 divided by 10. So that's just 36. So k is equal to 36. Next, we're going to find the value of c. So c is our vertical shift. This moves our function up or down c units. And c is actually also our axis of the curve. Now you can just look at the graph and identify the axis of the curve, but we do have a formula. Our equation is y equals our maximum plus our minimum, all divided by 2. So our maximum is 3, and our minimum is -1. And 3 plus -1 divided by 2 is just 1. So the value of c is a +1. And now let's identify d. So d is our horizontal shift. We would find d by just looking at our graph, but remember, we're doing a sine function and a cosine function. So we're finding two different values for d. Now it's going to depend on where you want your cycle to start. And just by looking at the graph, our graph starts at our maximum. So at 0, it's our maximum point, and our cosine function starts at the maximum. So again, since our graph starts at a maximum, that means there hasn't been any horizontal shift for the cosine function. So for cosine, d is equal to 0. But this is going to be different for the sine function. If there haven't been any reflections, our sine function starts at the axis of the curve and goes up to our maximum and then continues with its cycle. And on this graph, that is right over here. So our axis of the curve is at y equals 1 right here. So at our axis, our graph goes up to our maximum, back down, and continues with its cycle. And I'm just going to highlight that cycle. So our sine function has shifted over to the right, and that's 3 boxes. But how many units is that? Well, we know that 4 boxes is 10 units. So that means each box is 2.5 units, which means our sine curve has shifted to the right 7.5 units. So d is equal to 7.5. And these are not the only options. You could have had the cycle start right here and go down to our minimum, then back up. That would mean that we would have a vertical reflection, so your a value would be negative, and the value of d would change. Or you could actually extend this cycle back in the other direction and have it start here, so we have our sine curve right there. So whenever you're creating an equation, the value of d will always just depend on how or where you want your cycle to start. And now we're going to use all this information to write out our equation for our sine function and our cosine function. Now remember, this is our guideline that we're going to follow. But since this graph represents the height of a nail in terms of time, instead of y, we're going to use h at t. So this is going to be the sine function. So 2 is our a value. So this is 2 times sine. And then in brackets, our k value is 36. So remember, this k is always factored. Instead of using x, we're going to use t minus 7.5 because our d value is 7.5. And at the very end, plus 1. So that's our sine function, and we're really just substituting all of these letters with the values that we found, that we identified. So for the cosine function, everything is going to be the exact same except for d. So d is the only thing that's going to be different. So for the cosine function, we're going to do h at t equals 2 times the cosine of 36t. We don't have a d value because d is 0. And then at the end, again, we have plus 1. So this is our sine function and our cosine function that models this graph. In our next example, we have a sinusoidal function that has an amplitude of 2 units, a period of 180 degrees, and a maximum at the point 0, 3. So we need to determine the equation of this function and represent it with 2 different functions. So let's create a sine and a cosine function. But to help us, let's actually draw this function just to get an idea of what it looks like and to find out some other important key information. So we know that it has a maximum at the point 0, 3. So that's going to be right over here. And it has an amplitude of 2 units. So that would mean that the axis of the curve would be here, it would be 1. That would also mean that the minimum values are going to be at -1. Now, if it has a period of 180 degrees, so since the maximum starts at 0, 3, I can draw a cosine graph, one cycle of the cosine graph, and this is where 180 degrees would be. So there's the general equation for our sinusoidal function. Now always start off by identifying these key features of your function. So let's start off with A, our amplitude, and this is already actually given to us in the question. Our amplitude is 2 units, so we can just list that out. A is 2. But if you weren't given that, remember you can do your maximum minus your minimum and then divide it by 2, and that's your amplitude. And then let's find K. So you should know that the period is equal to 360 divided by K, and the period was given to us in this question. The period of this function is 180, so we need to use that to find K. So that means 180 is equal to 360 divided by K, so we need to solve for K. So K is just equal to 360 divided by 180, which means the value of K is equal to 2. And C is just our axis of the curve. So to find C, we can use our formula. So we need to do our maximum plus our minimum and then divide by 2. So we're just doing 3 plus -1 divided by 2, and that just means C's 1. And now we can find D. So D will depend on which function we're using, and we need to use sine and cos because we're being asked to find 2 different functions to represent this. Since our graph starts at a maximum, just like one cycle of the cosine function, that means our D value for the cosine function can be 0. And our sine curve starts at the axis of the curve and goes up, so we can make this one cycle of our sine curve. And we know that one cycle of a sinusoidal function is split into quarters. So since our cycle for this function is 180 degrees, I can split this 180 degrees into 4, like so, and that means that this sine function has been shifted to the right 135 degrees. So the value of D is 135. But again, you can have different options if you choose to make your cycle start somewhere else. So using all this information, I want you to pause the video and create 2 different equations to represent this function. So here are the 2 equations that I came up with, and you should have the same unless you chose a different value for D. Now we're going to write equations to model real-world situations. So in this example, a group of students are tracking Mr. Bueller riding a Ferris wheel. They know that he reaches a maximum height of 11 meters at 10 seconds, and then reaches a minimum height of 1 meter at 55 seconds. At the start of the ride, he was 10 meters off the ground. We need to graph one cycle of the height of Mr. Bueller off the ground in relation to time. We're just going to use this t-table to organize our information. So it says at the start of the ride he was 10 meters off the ground. So that means at the start that's 0 seconds and he's 10 meters off the ground. And it also says a maximum height of 11 meters at 10 seconds. So at time 10 seconds he's at 11 meters. And he also reaches a minimum height of 1 meter at 55 seconds. So 55 seconds, he's at 1 meter. And we want to know how long it takes to complete one cycle. So at 10 seconds, he's at the maximum of 11 meters. And then he completes half the cycle, half of the Ferris wheel at 55 seconds. He's at 1 meter. So how long did it take him to go back up to our maximum point? So from 10 seconds to 55 seconds, he goes from the maximum to the minimum, and this is 45 seconds. If we add another 45 seconds to that, we're going to be at 100 seconds. And he would go back up to the maximum point, so he would be up at 11 meters. So this means from our maximum point, where Mr. Bueller is on the Ferris wheel, for one whole cycle, for one whole revolution of the Ferris wheel, it takes 100 seconds for Mr. Bueller to reach the maximum once again. And now we can actually graph these points. So at 0, 10, that's where they actually start recording where Mr. Bueller is on the Ferris wheel. In 10 seconds and 11 meters, he reaches the maximum. in 55 seconds, that'd be halfway here, he reaches the minimum of 1 meter at 45 seconds, and then at 100 seconds, he's back up at our maximum of 11 meters. So this will be a little more than one cycle of the height of Mr. Bueller. So we made a table of values and drew a graph, and now we need to determine an equation that models the height of Mr. Bueller above the ground. So I want you to do this one on your own, or at least start it. Pause the video and find the values of A, K, C, and D so we can put that back into our equation. And when you're ready, come back to the video. Here's all the information I have. So A is our amplitude, and you find that by taking your maximum minus your minimum and divide it by 2. So that means our A value is 5. And our K, we find that by using our period. So our period is 90 because we knew that it took 45 seconds to go from our maximum to our minimum, and then another 45 seconds to go back up to our maximum. So one whole cycle is 90 seconds. So we need to do 90 equals 360 divided by K. And when we solve for K, we get that K is equal to 4. And our C value is just the axis of the curve. So we find that by taking our maximum plus our minimum and dividing it by 2. And that gives us that C is equal to 6. And D is our horizontal shift. So we need to go back to our graph to find out our horizontal shift. So here's our graph, and you need to decide if you want a sine function or a cosine function. Now for this graph, it makes more sense to use the cosine function because cosine starts at the maximum, and we already know where his maximum is. It's right here. So if I have one cycle starting at the maximum, that's one cycle of this function. And we know that Mr. Bueller reached the maximum at 10 seconds. So there's a horizontal shift of 10 seconds to the right. So our value for D, and this is for the cosine function, our value for D is 10. And now we need to use all that information to create our equation. So the height of Mr. Bueller in respect to time is equal to 5 times the cosine of 4 times t minus 10, and then plus 6 at the end. In part D, it asks us to determine Mr. Bueller's height at 78 seconds. So we can just use the equation we found in part B and substitute 78 seconds in for t. And when we calculate that, we get a height of 4.75 meters. And then it also asks us to determine when he reaches a height of 5 meters. So I want you to plug that into our equation and then solve for time. So if you're coming back to the video, you may have found one of the answers, you may have found none, or you may have realized there are actually 2 possible answers. So let's actually go back to our graph. If you notice in one cycle, at 5 meters, he hits 5 meters at 2 points. So we need to find the time at those 2 points. Now, if you started solving and just solved it regularly, you may have gotten one answer. Now I'm going to show you using our cast rule. At this point here, after I substituted and started isolating for t, at this point we get a negative ratio for cosine. And remember, I told you guys to never put in that negative ratio. Think of this as a triangle and always use the positive version. So if we have a negative cosine ratio, we have 2 possibilities for the cast rule. We're in quadrant 2 and quadrant 3. And I want you to find this related acute angle. So you need to do that by using the positive ratio. So if I do the cosine of, well, the inverse of cosine of 1 over 5, we're going to get 78.46. So that's beta. That's the angle for beta. That's the related acute angle. But to find our 2 angles, to find our standard angles, for this angle you have to do 180 minus 78.46, and I get an angle of 101.54. And then to find the second standard angle, you would have to do 180 plus 78.46, and you would get an angle of 258.46. So those are the two angles that you're going to work with. So we're going to do this twice, and we're going to use both angles. So first 101.54, and we're going to make it equal to this 4 times t minus 10. And now you just need to isolate for t, and when you do that, you're going to get that t is equal to 35.39. And then if we do it again with our second angle, so we make 258.46 equal to 4 times t minus 10. If we isolate for t, we're going to get that t is equal to 74.62. So in one revolution, Mr. Bueller reaches a height of 5 meters at 35.39 seconds and 74.62 seconds. In this question, I want you to try this on your own. For each what-if statement, you need to indicate how the function you created in part B would change. So you need to determine if the values for A, K, D, or C will change at all based on these what-if statements. So pause the video and try it on your own and come back to the video when you're ready. So if the wheel spun twice as fast, that means our period would be cut in half. So the period that we had was 90 seconds. And our period would just become 90 divided by 2, which is just 45 seconds. So that will change our K value. And our K value would actually double. Our K value becomes 8. If the base of the wheel was increased by 5 meters, then this moves our entire graph up 5 meters. So it affects our C value. So if we add 5 meters to our C value, that makes C equal to 11. Now what if our diameter of the wheel was increased by 10 meters? This is going to affect A, our amplitude. So our original maximum was at 11 meters, and let's increase that up by 10 meters. So our max is now 21 meters. Our minimum hasn't changed, still at 1 meter, and we need to find out our amplitude. So our amplitude is our max minus our min, divide that by 2, and we get 10. So our new value for A is 10.